In today's video, we'll learn about elastic collisions. We have learned prior that in inelastic collisions, our momentum is conserved but our kinetic energy was lost. However, in elastic collisions, both the momentum and the kinetic energy of the system of the two objects are conserved, giving a rise to the equation for the conservation of kinetic energy, which can be seen below. When we have two objects that collide and create a change in direction, and the momentum is conserved as well as its kinetic energy, we call this a glancing collision. Since there is a change in direction, there will be an x component and a y component. In the following example, it states that a billiard ball moving at 5 meters per second strikes a stationary ball of the same mass. After the collision, the first ball moves at 4.33 meters per second at an angle of 30 degrees with respect to the original line of motion. And in part A, we're asked to find the velocity and direction of the second ball after a collision. First, if we summarize the information we're given, it says that the mass of object 1 and the mass of object 2 are of the same mass, and that the initial velocity of object 1 is 5 meters per second, and its final velocity ended up being 4.3 meters per second, while the initial velocity of object 2 is 0 meters per second, since it states that the ball was stationary before the collision, and that the final velocity of object 2 is unknown, as well as its direction after the collision. So we can see that this is an unglancing collision and that we will have an x and a y component. So if we look at our x component first, our x component will be equal to the mass of object 1 times the initial velocity of object 1 plus the mass of 2 times the initial velocity of object 2 is equal to the mass of object 1 times the final velocity of object 1 plus the mass of object 2 times the final velocity of object 2. Since the mass of object 1 and object 2 are the same, we can ignore our mass variables in our equation. We can rewrite the equation. We'll have the initial velocity of object 1 was 5 meters per second plus the initial velocity of object 2 is 0 meters per second is equal to the final velocity of object 1, which is stated to be 4.33, and since we're acting in the x component, it'll be the final velocity times cosine of 30 degrees plus the final velocity of object 2, which is unknown, times cosine of theta. Since we're trying to solve for the final velocity of object 2 times the cosine of theta, we say it will be equal to negative 4.33 times cosine of 30 degrees plus 5 meters per second, which states that the final velocity of object 2 times the cosine of theta is equal to 1.25 meters per second. Since we solved for the x component, now we can solve for our y component. And since our masses can be ignored, we can write our equation where we can write that the initial velocity of object 1 plus the initial velocity of object 2 is equal to the final velocity of object 1 plus the final velocity of object 2. And since it states, since the velocity of object 1 was acting in the x direction, the velocity of object 1 in the y direction will be 0 meters per second. And since velocity of object 2 initially was stationary, it as well will be 0 meters per second, is equal to the final velocity of object 1, which was 4.33, and since we're acting in the y direction, we'll have the final velocity times the sine of 30 degrees plus the final velocity of object 2 times sine of theta. If we solve for the final velocity of object 2 times sine of theta, we'll see that it's equal to the negative 4.33 sine of 30 degrees, which can be simplified as being equal to negative 2.16 meters per second. Since we know the velocity in the x direction is 1.25 and the velocity in the y direction is a negative 2.16, we can solve for the missing angle by taking the tangent of theta times y over x. And if we solve for theta, we'll see that theta is equal to the inverse of tangent times negative 2.16 divided by 1.25, which will give us a value for theta as a negative 60 degrees. So we know the direction of object 2 after the collision. We can plug in our value for theta now, either into our equation for our x component or our equation for our y component to solve for the final velocity of object 2. If we plug it in to our equation for the final velocity in the x direction, we'll see that the final velocity times cosine of negative 60 degrees is equal to 1.25 meters per second, and we solve for our final velocity for object 2, we see it'll be equal to 1.25 divided by cosine of 60 degrees, or a final velocity as 2.5 meters per second. In part B, we're asked, was the collision inelastic or elastic? In order to figure this out, we must understand the definitions of an inelastic and an elastic collision. In an inelastic collision, the conservation of motion is conserved, but the kinetic energy is not. And in an elastic collision, the conservation of momentum is conserved as well as its kinetic energy. So by solving for the initial kinetic energy and its final kinetic energy and comparing the two values, we'll be able to tell if the collision was elastic or inelastic. So the initial kinetic energy can be expressed as 1/2 times the mass of object 1 times the initial velocity of object 1 squared plus 1/2 the mass of object 2 times the initial velocity of object 2 squared. And if we plug in the values we're given, and since our masses are the same, we can ignore the mass. So the initial velocity of object 1 was 5 meters per second squared plus 1/2 the initial velocity of object 2, which was 0 meters per second squared. And when we calculate this out, we see that the initial kinetic energy is equal to 12.5 joules. Now if we calculate the final kinetic energy, we see that 1/2 times the mass of object 1 times the final velocity of object 1 plus 1/2 the mass of object 2 times the final velocity of object 2. And we plug in the values we're giving and ignoring the masses, we can see that the final kinetic energy is equal to 1/2 our final velocity of object 1, which was 4.33 meters per second squared, plus 1/2 our final velocity of object 2, which was 2.5 meters per second squared. We'll see that our final kinetic energy is also 12.5 joules. And since our initial kinetic energy is equal to our final kinetic energy, we can say that this collision is an elastic one.